Alrighty gang, welcome back. In the last video, I showed you guys this Word document where I had some summary points from chapter 22, which is about electric fields. And I showed you guys some problems that I like, which are examples in the book. Today, I will solve them. So let's start with this first one. The hydrogen atom. The electron and proton of a hydrogen atom are separated on average by a distance of approximately 5.3 times 10 to the 11 meters. Find the magnitudes of the electric force and the gravitational force between the two particles. All right, solid. So it's nice to start off with a little picture. This is the nucleus, which is a proton, and here we have an electron. This distance here is a distance r is equal to 5.3 times 10 to the negative 11 meters. The charge of the electron is equal to negative 1.602 times 10 to the negative 19 coulombs. Is that correct? I'm going to ask my good old friend ChatGPT, charge of electron. Let's see what they give. Negative 1.602 times 10 to the negative 19 coulombs. Cool. Charge of the proton. I'm asking ChatGPT again just to confirm, but I'm positive it is the same except positive. Negative 19 coulombs. So this is a really small number. This times 10 to the negative 19. It's scientific notation. And the only difference is the proton is positive while the electron is negative. Mass of the electron. Mass of the proton. We're just going to write them here. Going to ask ChatGPT again. Mass is normally written in kilograms. And then another good thing to keep in mind is the electron is super small compared to the proton. So it is much smaller, times 10 to the negative 31 kilograms. 1.673 times 10 to the negative 27 kilograms. The bench PR. So we have these numbers here. Now let's remember Coulomb's force due to electric charged particles is Ke Coulomb's constant, charge 1 times charge 2 in the numerator, the distance between them squared. So this is just a magnitude equation. They're asking us in this problem for the magnitudes of the electric force and gravitational force. Let's actually write the gravitational force here. I'm going to ask ChatGPT again. They look very similar. There is a constant here. Here we have mass 1, mass 2 divided by the distance between them squared. Except the constant here is not Coulomb's constant. It is Newton's gravitational constant. You won't need to know this for the class, but it is good to know because it'll help us solve this problem here. So let's plug in the numbers. Coulomb's constant, I'm asking ChatGPT again because it is a nice service to use, but in a test you could just use your equation sheet, formula sheet, whatever. You should be able to have this 8.987 times 10 to the 9. The units here are Newton, meter squared, Coulomb squared. Cool. We multiply this by, well, this is asking us for the hydrogen atom. We're finding the force between these two guys. So we multiply by one thing, which is negative 1.602 times 10 to the negative 19 coulombs. I'm writing the units there as well because it's nice to have units. 1.602 times 10 to the negative 19 coulombs. And the distance we have here is 5.3 times 10 to the negative 11 meters, we square that entire thing. Awesome. Let's plug this into a calculator. And I actually don't have a calculator with me, so I'm going to calculate that in a second. Let's do the gravitational one. So the force due to gravity is gravitational constant G, which is 6.674. Very cool constant. Where did it come from? Who knows? Maybe God made it such. Oh, hold on. Oh, yeah. This is Newton meter squared over kilograms squared. We multiply that by, in the numerator, the masses. 1.673 times 10 to the negative 27 kilograms. Mass of the electron, 9.109 times 10 to the negative 31 kilograms. The distance is, again, the same distance, 5.3, 10 to the negative 11 meters squared. Nice. And as you'll see here in Coulomb's law, Coulomb's law, we have coulombs times coulombs there cancels with these two coulombs. Meter squared here cancels with these meters squared. By the way, I'm going to erase this little tak because we need to square that bottom thing. I just want to show you that the final thing for force here gives us units of newtons, which is what force is in. Same thing here, we have kilograms squared on the bottom, kilograms and kilograms here cancels. This meter squared cancels with this meter squared, and we get force of newtons. So I'm going to go get a calculator real quick, and I will calculate this FE and FG, and we will get an answer for this question here. Sounds good? Alrighty. Alright, I'm back, and I'm actually going to calculate these on video to show you guys that it's not that crazy using a calculator. Sometimes people get a bit spooked. So we have 8.987. I'm going to do E, which is the times 10 to the 9. Multiply that entire thing by, I'm going to do 1.602 times 10 to the negative 19. That entire thing squared, because we're multiplying them by the same number. Divide by 5.3 times 10 to the negative 11. That entire thing squared as well. Holy, we got a small number. And we have a minus sign. So here I have 8.2 times 10 to the... can I convert this to scientific notation? Let me see. Shit, I think I just erased my... I just erased. Hold up, guys. Okay, I'm going to rewrite that entire thing. 8.987 times 10 to the 9 times this thing squared divided by this thing squared. And then I have 5.3 times 10 to the negative 11. Okay, 8.21 times 10 to the negative 8. And I already did all the unit analysis, so we have newtons. Awesome. Now let's plug in everything for the gravitational law. So I have 6.674 times 10 to the negative 11. Multiply that by... Now we can't square nothing because we have two things that are different. 1.673 times 10 to the negative 27. Close bracket times open bracket 9.109. My bad, y'all. 9.109 times 10 to the negative 31. Close bracket divided by open bracket 5.3 times 10 to the negative 11. Close bracket, square, boom. Oh man. 3.6 whoops, that is not a 6. 6.2 times 10 to the negative 47 newtons. All right, so the reason they make you do this problem is 1, so you can plug numbers in and see how Coulomb's law works, and 2, to see that the electric force is much stronger than the gravitational force. The second part of this problem, they actually ask you to take the ratio, this divided by this, to see how strong the electric force is compared to the gravitational, or to take their ratio. And the ratio here is, I want to do, also this minus sign here is important. Minus sign in electrostatics means an attractive force. In gravity, it's always positive because masses are always positive, so gravity is always an attractive force. There's no repulsive gravity. But in electrostatics, if you have a positive sign, it means repulsion. If you have a negative sign, it means attraction. So let's see here. Oh, also you can see that from this thing here. If you have a plus and a plus, you get a plus sign at the front. Positive times positive equals a positive. That means a repulsive force. If you have a negative and a negative, you get a positive, which is also a repulsive force. But if you have opposites, like this plus and that is minus, then you get a minus, attractive force. Or if it's vice versa, then you get a minus, which is an attractive force. Units are also very nice to look at because they help you confirm if your answer is correct or not. So let's plug this in. We got 8.21 times 10 to the minus 8 divided by 3.62 times 10 to the minus 47. We get this number 2. And by the way, once you take this ratio, the newtons cancel. So you get just a ratio, a unitless thing. 2.27 times 10 to the 39. That's crazy. So let's say we want to multiply FE, or both sides by FG. We get FG times this 2.27 times 10 to the 39. What this is telling you is that the gravitational force has to be multiplied by this ginormous number in order to equate to the electric force. That means the electric force is this factor stronger than the gravitational force, which is a cool thing. I mean, that's also in the scenario here when you have really tiny masses, but you can see that the electric force is just much stronger once you're dealing on these like tiny length scales here. Gravity only starts becoming powerful once you conglomerate a bunch of stuff together, like the mass of a planet and a sun. And also, what's interesting is at that stage, when you have so many particles together, like think about how many electrons and protons are in the Earth and in the sun. At that stage, when you combine all those together, they pretty much all cancel out and you get a neutral object. Like Earth is like overall, I would say neutral. I mean, I haven't done any studies on that, but Earth and the sun are neutral. So the electric force between those two guys is pretty much negligible. So it's cool to see the scales of things working here. Anywho, that is this problem here. We solved it in like one page. Looks pretty good. I hope you guys learned something cool from it. Let's move on to this second problem, which deals with vectors. So we got find the resultant force. Consider 3-point charges located at the corners of a right triangle, as shown in figure 22.8 over here on the side. Q1 equals Q3, 5 microcoulombs. Q2 is minus 2 microcoulombs. So we have 2 positive charges and 1 negative charge. They're not electrons or protons. They're just charged particles because they have microcoulombs instead of the charge of the proton and the electron, which I showed you guys here. So that is a problem that you guys would see in some of your problems. Find the resultant force exerted on Q3. And very nicely, they show us a picture here. So I'm going to redraw this picture over here just to show you guys what's going on. We have this guy, which is Q3. Q3. This is plus, right? Over here, it has a minus charge, and over here, it has a plus charge. Q2, Q1. Coulomb's law works on a line conjoining these two guys. So you can find the force acting on these two guys. And since we have a positive charge here and a positive charge here, this will be a repulsive force. And over here, since you have a negative charge and a positive charge, this will be an attractive force. I'm just drawing the force lines. Here I'll do F minus, here I'll do F plus. Oh, this one I'll do in red. Whatever, keep it nice. And I'm just drawing them on this thing because that is the question. Find the resultant force exerted on Q3. You can also draw the corresponding things here, but for this problem, it doesn't really matter. So let's find these charges or these forces. Well, first of all, it is the same thing as what we had before, this equation here, right? So let me just copy this equation. We have charged particles. In this case, we have a repulsive force and an attractive force. So we're going to do it separately. Let's start with the first one. I'll use black ink here. F positive. KE, sorry. We have here Q3 times Q1 over R31 squared. Awesome. Let's already plug in some numbers. So I'm going to scroll back here to see what Coulomb's constant was. It was 8.987. Times 10 to the 9 Newton Coulomb squared per meter squared. Please always write your units. Also, I'm going to put this guy over here so I have some room to work with. And we're going to plug in the charges of each of them. So here I said Q3. We're going to look at Q3. Q3 is equal to 5 microcoulombs. 5.00. Micro can be replaced by this. Let me just confirm that with ChatGPT. I literally wrote micro is what scientific notation? Let's see if it understands my question. The prefix micro, symbol mu, this guy, is equal to times 10 to the minus 6. So after a couple of times doing this, you will get used to it. So that's microcoulombs. 5 times 10 to the minus 6. Coulombs is equal to 5 microcoulombs. That is a positive charge because it's Q3. And we are dealing with the positive force. So here we have Q1, which is also 5 microcoulombs. So instead of writing that, I'm just going to put a squared here because it's the same charge. Here we have the distance that separates them, which is, they actually give it to us, square root of 2a. And a is given to us here in meters. So I'm going to put square root 2 times 0.100 meters. Please use your units. Remember that all of this is squared because Coulomb's law has r squared here on the bottom. We're looking good. I'm going to equate this. Again, look at the units. Units cancel out nice. Here we have, wait a second. The units of this guy are meters squared on the top and Coulomb squared on the bottom. You see? Unit analysis prevails. Newton meter squared, Coulomb squared. So what I was saying before is we have Coulomb squared on the top, Coulomb squared on the bottom cancels, meter squared on the bottom, meter squared on the top cancels. The force is given to us in newtons. Amazing. Let's plug all of these numbers in together. 8.987 times 10 to the 9 times, open bracket, 5 times 10 to the minus 6, close bracket, squared, divided by open bracket. We have a square root 2. I'm going to multiply the square root 2. The square root is only on the 2, not on the a. So multiply that entire square root 2 by 0.1, close bracket, square that bad boy, equals, and we get a force of this is 11.23 newtons. Great. That is for F plus. Now let's do F minus. F minus is equal to KE Q3, because Q3 is the one being acted on, Q2 R32 squared equals 8.987 times 10 to the 9 Newton meters squared Coulomb squared. Over here on the top we have Q3, which is 5 times 10 to the minus 6 coulombs. Q2 is actually a negative charge, minus 2 microcoulombs, which is times 10 to the minus 6 coulombs. On the bottom, we have another distance, which is A, 0.100 meters squared. Let's confirm that. The distance between Q3 and Q2 is A. Correct. Equal sign down here. Let's check the units again. Coulombs is Coulomb squared on the top, cancels with Coulomb squared on the bottom. Meter squared cancels with this meter squared. We get newtons, which is the correct unit we're looking for. Now let's plug everything in. 8.987 times 10 to the 9 times, I'm going to do open brackets and stuff because I have little scientific notation. I don't want anything to get messed up. 5 times 10 to the minus 6 close bracket times open bracket minus 2 times 10 to the minus 6 close bracket divided by open bracket 0.1 close bracket squared, boom. And we get a minus sign, which is correct because it is an attractive force. And we also have a minus sign right here, which has no other minus sign to cancel with. So we get 8.987 newtons for the minus force. Now, are we done the problem? No, we're not. It says find the resultant force on Q3. At this stage, what we have is a free body diagram. We have these forces acting on Q3. So one force is going this way. This is the repulsive positive force. Positive meaning between positive charges. We have another force which is here horizontal, which is the attractive negative force. And we calculated this to be, here is minus 8.987 newtons. Here it is 11.23 newtons. Okay, so what we're going to do here, y'all, is we're going to break apart this vector into components and add those components up to find one vector that will equal the resultant force. If you just look at these two vectors, what we want to do is add them up. So I'm going to copy these bad boys here. Paste them here. And let's say we want to add them up. So I'm going to separate them like this. We want to do this plus this equals. And literally what you do with vectors is you take one vector, let's say it's the first vector, we'll set it up like this, and then you take the second vector and line it up at the tip of the first vector. So we get something like this. Now the resultant vector is from the starting point till the end point, you create another vector. So in fact, the answer, the resultant vector, is just this red vector here. So it is going somewhere in the up and to the left a little bit. Up and to the left. Maybe. Unless I drew them a little bit. I drew them a little bit off scale. This vector is actually smaller than this vector because it has a length of 8. This vector has a length of 11. But the actual addition of vectors looks like this. How we're going to do it, though, is we're going to break them apart a little bit more systematically. We're going to break them up into components. And how we do that is paste. Well, let's say we drew a x and y axis right here at the point that we're talking about. So we have x here, y here. You can see that this guy is here in the negative x direction. We have, well, it's a negative force pulling it that way, but it's also drawn like this in the negative x-axis. Whatever way you want to think about it. It's almost 9 newtons, 8.987 newtons, and I will put a little x hat there. All right. This vector here is a little bit different. We would like to break this vector apart into its x and y components like this. So I'm going to use this. Orange here. It's going to be broken up into this vector pointing directly in the y-axis and this vector in the x-axis. Now take a look at this. If I take a vector like this and combine it with a vector like that, the way this looks, we use the same color, is literally the vector addition I did before. This plus this. You take the starting point here, the ending point there, boom. And we get the same vector as before. You see what I mean? Or you can do it backwards. You have this vector here. You can decompose it into its component vectors like that. That's why I drew those little dotted lines like this. So you can break apart a vector into its components, or you can use its components to get the resultant vector. What we're going to do in this scenario here, this right here, is we're going to break apart all the vectors that are going in the middle of the x and y plane like this. We're going to break them apart into components going just in the x and just in the y. And then we're going to combine all of those together to get the final resultant vector. Now, how do we do that? It's a little crazy. Let's look at the picture here. Let's think a little bit. I'm thinking. Let's take a screenshot of this and think on another page. Take a screenshot of this. What the fuck? Okay, let's copy, paste. How do I crop this bad boy? Crop. We're gonna crop this just to look at the picture, right? I'm thinking with you guys here, I'm thinking. So what I'm looking at is we have a triangle. It is a right angle triangle. Here is the right angle. This angle is equal to 90 degrees. And, well, it's a square. Here we have side length A. Here we have side length A. So I know that this is equal to 45 degrees. How do I know that? Well, if I have a square like this. Oh, that is not a square. This is a square. And I write a line right between here. I know that this guy is 45 degrees, this guy is 45 degrees, and this guy is 90. Because that's the only way it could work. By the way, if you add up all the angles in a triangle, here we have 90 degrees, which is this one here, plus 45 degrees, plus 45 degrees. You will always get the sum of the interior angles of a triangle to be 180 degrees. 90 plus 45 plus 45, both these 45s equal to 90. And 90 plus 90 equals 180. Why does this work? Guys, I don't know. You gotta ask the original Socratics or Pythagoras, one of those old school dudes that were dealing with triangles. Interior angles of any triangle, not just right angles. Not just right triangles. Any triangle. Interior angles of any triangle equal 180. The sum of interior angles. Okay, so why is that important? Well, here I know that's 45, and I know this is a right angle, so 45 plus 45 is equal to 90. This is a bit of trigonometry, a bit of geometry with triangles, trigonometry. And solid. So we have 90 here, we have 45 here. This should also be 45. Why is this helpful? I'm trying to find this angle here. And this angle looks like it's also 45. Why is that the case? Well, take a look at this. I have a straight line like this. And I cut it with another horizontal line. The cut that I make will make two angles here, theta 1, theta 1. These two are equal. And two other angles, theta 2, theta 2. This will always happen. You'll always have two angles that are the same. That's why when I look at this picture here, this angle 45 helps me find this angle that's 45. And why is that helpful? Look at this little image right here. What we have there is our vector in question, f which is the repulsive positive vector. We have some horizontal line like this, which is the horizontal line that is dotted right here. And we are given an angle theta equals 45 degrees between that. If you have this scenario here, then you are good to go because you can break apart the vector into its components like this. I'm gonna show you how to do that in just a second. Let's erase this here. I hope that made sense with you guys. If it doesn't make sense, don't worry, just watch this video, enjoy, get some popcorn. The more you see stuff like this, the more it'll become a bit, intuitive. It'll make sense in your head. But for now, I'm just rushing through this so I can get a video that is not 2 hours long. So we have 45 degrees here. We also, from the first part of the problem, we found the force. I called this the positive repulsive force. It is equal to 11.23 newtons. Now, this is all of the components that a vector has. Vectors have a angle, vectors have a direction. We know everything we need about this component, this vector. So if we have a magnitude and a direction, then we can also break it down into components. So we can break it down into x and y components. So you can see a vector written like this sometimes, you can see a vector written like this sometimes. Vectors, sorry about that, have magnitude and direction, but they can also be broken down into small components, Cartesian components. I think the first dude that dealt with this was René Descartes. That's why Descartes, we call it Cartesian coordinates, Descartes. I literally could be making this up. Let me ask ChatGPT. Who created the Cartesian coordinate system? Let's see what baby girl says. The Cartesian coordinate system was created by French mathematician and philosopher René Descartes in the 17th century. He introduced this system in his work La Géométrie, which was published in 1637 as an appendix to his famous text Discourse on the Methods. Descartes' system allowed for the representation of geometric shapes using algebraic equations and is the foundation of modern analytic geometry. Literally W. Descartes. All right, guys, let's decompose this guy into its components. And the way we do this is by using sines and cosines. Oh my goodness, another thing we're learning here. I'm gonna paste this over here. I'm gonna erase this, move this over here. And let's say we're gonna use good old Descartes and we're gonna put this information down here. And whoops, I'm actually going to put this information over here to the side. Now I'm going to create a Cartesian coordinate system onto just this vector. Again, remember the end objective is to break apart this vector into its components. So here we have an x and a y. Let's say I take a big bar flashlight and I'm shooting light at this thing like here. What I create is the first kind of thing that I showed you guys. I create a dotted line here and I break apart this part of the vector, which is the y component. Now let's say I erase this block of light and I create a similar block of light shining up here, like that. I will create the x component of this vector. This is how I think about breaking apart a vector into its components. These two vectors combined to create this vector here. I think about it using the light bar, but the actual thing that is doing the mechanics under this is sines and cosines. So you may have seen a triangle written like this before. Right angle triangle, this is the hypotenuse. You can think about this angle here, and the opposite of this angle is this leg. Opposite. The adjacent is this leg. Adjacent. And then this is the hypotenuse. So you may remember sines and cosines of a triangle are sometimes introduced like this. So, ka, toa. This is tangent. Tangent we will not use too much today. We're going to focus on to these guys here. So, awesome. What are we looking for? We're actually looking for the opposite side and the adjacent side, because the opposite side of this angle, which remember it's 45. Also remember we have the hypotenuse. This is the hypotenuse. We have the length of the vector. So what we're looking for is actually the opposite side, which is this. Again, it is the same as this. They're both the same vectors. You just got to look at triangles wherever you see them. And the adjacent side is this guy down here, which could also be seen as this guy. So this is why sines and cosines are useful, because we can create this equation here. We can take sine of the angle theta is equal to O over H, opposite over hypotenuse. In this case, what is the opposite? Opposite is equal to this leg here, which I will say is the Fy component, or it is the same thing as this here, Fy component. That's why I talked about this bar of light that shoots light here. So we can create that, and well, we don't have O, but we can replace it with this variable Fy. We do have H. H is F positive, the positive force that we calculated, and we actually have a number for that. This is 11.23 newtons. Keep your units, guys. Please take a look at the units there. Okay, now what do? Well, we can also replace this sign. I'm going to write another thing. Sine of 45 degrees. Why can we replace that? Because we have the angle right here. We're talking about the angle. Okay. Now we can create an equation by just multiplying this 11.23 on both sides, and we can get Fy on one side is equal to 11.23 newtons, keep your units, times sine of 45 degrees. That is sick. Why is that sick? Because if you plug in sine of 45 degrees in your calculator, make sure that shit is in degrees and not radians. Let's do I have degrees? Sine of 45 is equal to, I don't think I have the correct setup here. I'm going to do degrees. Sine of 45 degrees. Degrees are not the same as radians. So what I get is 11.23 newtons times square root of 2 over 2. This thing is equal to sine of 45. Okay, nice. So now we literally have Fy is equal to square root of 2 over 2 times 11.23. And this thing, square root of 2 over 2, is unitless. You know why it's unitless? Because sine of cosine, or sine and cosine and tangent are defined as this function that eats an angle, and it gives you O divided by H. What is O divided by H? Opposite, it is a length. This is the length of a triangle, over H, which is a length. Units of length divided by length, these things cancel and they give you a unitless thing. That's why sine and cosine is a unitless thing. It gives you something with no units, like a percentage. That's why root 2 over 2 is a unitless thing. That's why these units are important to keep, because you have units of newtons on one side, and you're looking for the force on the y component on this side. Man, solving this problem is quite long, but it's important. You guys will see how this leads into other problems. I think if you know how to do this, you'll be able to break apart vectors very nicely. So what did this get us? This got us a number, 7.941 newtons. This is the component of this vector, in the y direction. Alrighty, and that was sine, okay? Now let's take cosine. We can do the same thing. What is cosine? We take cosine, we put a theta in it, because cosine is a function that eats an angle. And cosine, using the SOHCAHTOA mnemonic, is adjacent over hypotenuse. So I'm going to write A over H. What is A in our triangle? Adjacent is adjacent to this angle. It is this thing right here. This thing right here is F subscript X. You can also think about it as this thing right here, right? If the angle here, theta, then this is the adjacent Fx. It just depends how you're looking at the triangle. So adjacent is literally Fx. Hypotenuse is again the positive force that we calculated in the beginning of this problem. So we have that number as 11.23 newtons. Again, we can plug in cosine of 45 degrees because we have that angle. We can multiply both sides by this 11.23, and we can get an equation for f of x is equal to 11.23 newtons times cosine of 45 degrees. What is that cosine 45 degrees? Look at that, it's root 2 over 2, the same thing, which is actually equal to 7.941 newtons. That's interesting. It's actually the same thing. Why is it the same thing? Well, it's good to ask yourself what's going on here. Why are these components the same? Let's calculate it. It is the same thing. You got to ask yourself, why is it the same thing? Well, go back to the original thing we were looking for. I know this picture is messy now, but this is what we're looking at, this picture here. So if you take a look at this angle is 45 degrees. This vector is going up here. So if you break it down into its components, it's literally like a square. And the side lengths of a square are going to be equal. This is equal to this. So it makes sense why these are equal. This only works if your right angle triangle has 45 degrees. If this angle was something smaller, like we had something like this, and here it was 30 degrees, then of course you would have different components. This component would be smaller, the Fy, and this component, the Fx, would be larger, Fx. So it depends what your triangle is looking like. Okay, I hope that made sense, guys. Anyway, now let's redraw our free body diagram. We now have two components. This one, F subscript x is equal to 7.941 newtons. We're talking about force. This one, Fy equals the same thing, 941 newtons. Remember, this was how we broke apart this vector, the positive repulsive force, this vector here. We broke it down. And why do we break it down? Well, we broke this vector down. This vector we didn't need to break down, so I'm going to draw that vector here. This was the original vector. F minus, this guy is equal to, what do we say it was equal to before? This number, negative 8.987. 8.987 newtons. Now, it's very cool because we can find the total resultant vector, F tot, acting on, remember that was the original question, find the resultant force exerted on Q3. You can imagine like Q3 is this tiny ball being pulled in this direction and in this direction. So its resultant force should be somewhere here, right? It's going to start traveling that way because it is being repelled by this charge and is being attracted by this charge. So it'll be pushed somewhere in the upper left direction. Let's confirm that by finding the resultant vector. And now that we have everything in components, we can actually find it very easily. What is the addition of vector quantities in the x direction? Well, we have this 7.941 in the positive x direction, and we have this thing pulling it in the negative x direction. So we have literally in your calculator 7.941 newtons plus, you can do a plus, but here notice it is a negative, so technically it is minus, right? Because in the negative direction we have a stronger force. Negative 8.987. When you add those two up, 7.941 minus 8.987, we get minus 1.046. And in the y direction, we actually don't have to add anything up. This is the only force in the y direction. 7.941. Y direction, y hat. This is the final answer, except it's written in this form that people don't see too much with the Cartesian coordinates. Let's do exactly what we did over here, except instead of breaking it apart using its components, we use its components to add them up together to find the resultant force. How do we do that? Well, this is very nice. We can draw another Cartesian coordinate system here. This is the x, this is the y. Let's draw the components. So we have 7, a very big vector, which is almost 7.941 newtons in the y direction. And then minus 1, minus 1.046 newtons. Now look at this. Let's combine these two vectors. And the way you can combine them is by, well, you can draw another vector right here. That is the y. Draw another vector here. And the middle line, or the middle line of these two, is the combination of these two is somewhere here, like that. Another way of looking at this is like draw these two legs of the triangle. So here we have one leg, here we have another leg. Let's say we draw this hypotenuse here. This is a right angle because it is a Cartesian coordinate system. Minus 1.046 newtons. Here we have 7.941 newtons. And we're looking for this vector, right? Are we looking for this vector? Yeah, you can create this triangle here. This triangle here. That'll give you the magnitude of this vector. But technically, the direction of this vector is actually here. So the way you add up these vectors is you actually have, let's say you have two vectors like this. Boom, boom. Remember how I told you you can take one and line it up tip to tail, like that. And then you can take the starting point to the ending point. This here will give you the vector. You can also do it a different way. You can take tip to tail the other way. So let's take this guy and bring it back here. And let's instead take tip to tail this guy. Boom, you get the same thing. So if you do that both directions, let's say we have both of these guys. Copy these guys. Paste. I'm just going to delete this vector here. Delete that. So I can take this vector, put it back here, and I can line up tip to tail both ways, and I create kind of this nice little cube here, or this nice little rectangle. So that's why I drew the vector like this here, because it is going in this direction. But if you draw a triangle like this, it's basically asking you Pythagorean theorem to find C, which is this thing. So you have c squared equals a squared plus b squared, Pythagorean theorem. And how do you do that? Well, let's say a is here and b is here. Don't worry about this minus sign because anything squared removes the minus sign. So we have 1.046 newtons. Remember your units, guys. Don't worry about units. Don't worry about them. They're actually very helpful. 9.40. Let's pray I'm still recording audio. I've been going for a hot minute here, guys. Okay, 9.041 newtons squared. This gives you, let's plug it into the calculator, 1.046 squared plus 7.941 squared equals 64.1. And that means C is equal to square root of 64.1, which is equal to 64.153. You know, some other numbers, doesn't matter. This gives me almost exactly 8.00 newtons. So that means this side, C, is equal to 8 newtons, 8.00. That means this vector has a strength of 8 newtons going in this upwards direction, which is the direction I guessed it would be going, right? You can imagine a little ball being pulled in this direction, a little ball being pulled in this direction. You would get something kind of in the middle of here. I mean, you can also do that tip to tail thing here. Combine these vectors like that, you would get the vector in the middle. And this would be 8 newtons. Now, one cool thing you can do with this is actually, let's say you want to find the angle here, the angle. This is actually when you use TOA. Remember when I did SOHCAHTOA and I told you we wouldn't use tangent? Well, in this case, you have opposite, which is, let's say you want to find this angle here. You have opposite, which is op here, adjacent, which is adjacent here, and you're looking for hypotenuse. You would use this guy and tangent, and then you can find reverse engineer and find the angle between those guys. In this case, I just found the magnitude of the vector. You know what, man? For my viewers, let's actually find the angle of that vector. So, okay, what we found was that the resultant force of this vector is 8 newtons, we found out that its components here were minus 1.046 newtons. We found the components going in this direction. This was 7.941 newtons. Let's say we want to find this angle here. Keep in mind though, normally when you have vectors, the angle is taken from the positive x-axis here to the vector itself. So if our vector is pointing in the negative x-axis, the angle would be all the way here. Boom, this thing. In this case, I'm just using the triangle like this, so I'm calculating this angle here, theta 3, let's say, theta 3. This is theta 2, theta 1. So actually what I would want to find is theta 3 and then do 180 degrees, which is this entire distance here. And then I would do minus theta 3. Then I would find this is equal to theta 2. That would be the original convention. Conventionally, angles like this are found from the positive x-axis to the vector in question. In our case, the vector in question is here. So from the positive axis to the vector in question, we are looking for this theta 2. So I would need to do this. If I want to find theta 3 first, theta 3 is given to me by this, from the negative x-axis to here. So just keep in mind how you're setting up the problem, what you're looking for. Anywho, since I did Pythagorean's theorem here, I actually found the hypotenuse. So technically I can use any one of these because now I have O, I have A, which were the original things given to me here, and I calculated H. But let's say we want to be fancy and we want to use tangent because we haven't used tangent yet. So I'm going to erase this. Let's say I don't know the hypotenuse. This is the hypotenuse. The angle here that I'm given, hypotenuse, the angle here that I'm given is skaboomp. We create this triangle. So this would be Fy. This here would be Fx. This is theta. This is H. So Fy here is equal to the opposite side of the triangle. Fx is the adjacent side. So if I want to use TOA, I say tangent theta is equal to O over A. This is what the mnemonic is telling you. What is O and what is A? O is opposite, which is 7.941 newtons. And then here we have minus 1.0. This is the crazy thing, guys. If you plug in minus, you might actually get the correct answer of theta equals 2 without doing this step here. But since I'm doing it a little bit roundabout, I'm going to remove this minus sign here. I'm going to change it to a plus. Because when I deal with triangles, I like dealing with positive quantities. I like dealing with lengths. Lengths are always positive. It's not too important for this class. Just if you want to take a look at it a little bit more, you can take a look at how tangent function works or stuff like that. But let's say we have this number here, newtons. Keep in mind, if you keep your units, newtons cancels with newtons. This whole thing is a unitless value. This whole thing is a unitless value. Tangent of theta, theta has units of degrees. This whole tangent thing is a unitless value. Pretty cool thing. I like thinking about tangent, sine, and cosine as like percentage functions. So anyway, at this stage, what we have is a ratio. And what we're actually looking for is theta, because we don't know theta. Now let's calculate what 7.941 divided by 1.046 is equal to. And it is equal to 7.59. Hold on a second. Opposite over hypotenuse. Opposite. Did I mess something up? It just feels like I messed something up. 7.959, let's do 2. 7.592, this is unitless. And now, if we want to find theta, then we have to take tangent inverse of both sides. Tangent inverse cancels with tangent inverse. On the other side, what we have is tangent inverse, an inverse tangent function of this thing here. And let's plug that into the calculator. Tangent inverse, strange function. Some calculators can do it pretty easily. Other calculators kind of struggle with it. What we get is 82.49. And now this is degrees because what we're talking about is theta. So if that is theta 2, or sorry, theta 3, then I do 180 minus that. 180 degrees minus 82.49 equals 180 minus 82.49 degrees, 97.51 degrees. Amazing. So the resultant vector is equal to 97.51 degrees. The magnitude here is 8.00 newtons, or you can write it into its component form, which is minus 1.046 x hat, the x direction, plus the y component, which is 7.941. 941 newtons in the y hat direction. Also, I should have put newtons here, newtons right there. This is two ways to answer this question. The first way, which is the thing you will mostly use in this class, is components. Component form. This is magnitude and direction. They're equivalent. They're vectors. Let's actually check if this is correct in the book. In the book, scroll all the way up here. One of the very first problems that they do. Here it is. Okay, they go through on their solution, blah, blah, blah. Boom! That looks familiar. Negative 1.04, 7.94, negative 1.04, 7.94. I even had a bit more significant figures in there. Oh, this is my Word document. We have that. Now, let's see if they actually show it to us in... They don't even show the magnitude. No, they don't show the degree, the angle, and the direction. They don't show this, so this is an extra step that I want to show you guys. All right, cool. Now the next problem we will do is this problem here. But what I want to do is first pause a little bit to make sure my microphone here will not die, and then I'm up. All right, gang. Welcome back. This is the problem we're doing here. Two identical small charged spheres, each having a mass of 3.00 times 10 to the minus 2 kilograms, hang in equilibrium as shown in figure this one. The length L of each string is 0.150 meters, and the angle is 5 degrees. Find the magnitude of the charge on the sphere. So I'm going to try to go through this problem a little quicker, but basically, they show us here a picture of all the forces acting on this charged, on this single charged particle, this one. It's like they blew up the image here and showed it to you. So on both spheres, you have F equals ma equals mg, the force of gravity. So that is on both of them here. And you can calculate that using just mass times g, which is 9.81. So that is a vector pointing downwards. You also have the spheres repelling each other, which is shown over here with this Fe. They repel each other because they are positively charged. And the final force acting on both of these guys is the force of tension due to the string. So they drew here a single free body diagram of one of the spheres, and they show you basically the same thing I showed you just a second ago, how you can break up this force vector of the tension into its components. And they actually did it for you. Here, it's T, the magnitude of the tension vector, multiplied by cosine theta. In this case, theta is this angle here. And here you get the other one, sine theta. So they actually give that to you. If they don't give it to you, it's your objective to break this vector down into its own components. But keeping that in mind, the next thing that's important is this sphere is in equilibrium. So equilibrium means F equals ma, Newton's second law, is equal to 0. Since this is equal to 0, you know that these forces must cancel out. There must be a force acting this way, a force acting this way. They cancel each other out perfectly. There must be a force acting this way, acting this way. They must cancel each other out perfectly. There must be equal and opposite forces canceling each other out. If not, if this force does not equal 0, then this acceleration does not equal 0. And if acceleration does not equal 0, then you know the object is moving in some direction. In this case, the object is not moving. They are in equilibrium. And from that, what you can say is the forces acting here, we have T cosine theta. Here we have the mass gravitational force, which is mg. They put a little vector on the g, doesn't matter too much. Here we have T sine theta, and here we have Fe. Okay, so what this equilibrium thing is telling you is basically that Fg must be equal to the vertical tension force, and Fe must be equal to the horizontal tension force. Basically what I'm telling you is this force must exactly equal this force, and this force must exactly equal this force. If they don't equal, again, F does not equal 0, which means from Newton's second law, ma does not equal 0. And that means there is acceleration and the system is moving in some direction. In this case, this word equilibrium is very important, and it tells you that these things equate in such a way so that you can create these two equations here. So if you can get to this stage, you're absolutely booling, because what you can do from here is solve for Fe. If you remember, Fe, I'm going to write it on this side of the equation, is Coulomb's law, Ke. Q, in this case, Q is, well, they tell you that the spheres have a charge Q, and the question is actually find the magnitude of the charge on the spheres. So what we want to find is Q. Since we know both of them are positive, there's a positive Q here, positive Q here, so they combine to give you Q squared because they're equal. Coulomb's law also has this R squared, and boom, we can create this equation here. If everybody is comfortable with that, then, well, what do we do next? We have this value, Ke. We have R because they give us A, so R between these two is just 2A, right? What we don't have is this tension. So what do we do? Well, we can calculate T from this equation here. We know that Fg is given to us as mg, which is equal to the mass of the thing, of the ball, 3 times 10 to the negative 2 kilograms, and g is 9.81 meters per second squared. Cool. So I'm going to write another equation here. Fg is equal to 3 times 10 to the negative 2 kilograms times 9.81 meters per second squared. This is equal to T cosine of, they tell us it's actually cosine theta, and they tell us theta is 5 degrees. So I'm going to just literally put that in there. Now let's solve for T, because we're looking for T. So T is equal to, just divide this cosine, put it on that side. And let's actually calculate this thing here. So I'm going to plug into my calculator 3 times 10 to the negative 2 times 9.81. That gives me 0.2943. This is kilograms meters second squared. And we divide this whole thing by cosine of 5 degrees. What is cosine of 5 degrees? It is, I'm going to just erase this, 0.99619. Whatever. Let's calculate that. 0.2943 divided by 0.99619. Basically the same number because we're dividing by something very close to 1. 0.2954. Okay, slightly different. Again, units kilograms meters second squared. What are these units? These are SI units, and if you remember, well, where did we get these units from? We got it from this, which is mass, and this, which is G, or we got it from MA. What is MA? F equals MA. If M is kilograms, put them in square brackets, and A is meters per second squared, classic acceleration, you know F here is in units of newtons. So you know kilogram meters per second squared, this unit here, is equal to newtons. So nice, I literally calculated tension, like just by doing that with one equation. Alrighty, so now we can plug this into this equation. So what we have is T sine theta. Let's already just plug this in. 0.2954 newtons times sine of theta is sine of 5 degrees, right? Am I tripping? Sine of 5 degrees, 5.00, which is 0.0872. Put a 2 there. Am I still recording audio? I am still recording audio. I just got a phone call here. Sorry about that. What's on the other side of the equation? We have KE, we have Q squared, and R squared we actually know. It is A. A is equal to 0.15 meters. 1.5 meters squared. This equation here. Let's calculate this number here. This is 0.2954 times 0.0872. Remember, units, please carry them over. They are going to help you in the long run. 0.025. Let's do 76 newtons around that. KE. What is KE? Let me check my chat GPT real quick. 8.987 times 10 to the 9 newtons here, meters squared, coulombs squared. Here we have Q squared because we don't know what it is. Here we have 0.15, that is squared. So what we have is 0.0225 meters squared. Remember, because we squared the meters. Now let's cancel some units. We have meters squared on the top, we have meters squared on the bottom. We have newtons on this side and newtons on this side. Divide both sides by newtons, we get that. We have something that's unitless over here, which you guys might find weird, but here we have coulomb squared, here we have coulomb squared. These cancel to give you something unitless, but we're not going to cancel those yet because what we're looking for is Q. So once we multiply this by here, we have this in the numerator, coulomb squared, and that gives us the proper units for this. So that was a little too quick for you. No worries, just follow out the units, make sure you write the units. The units will help you get the right answer at the end. So what we're solving for is Q. Let's isolate for Q. We have Q squared is equal to, let me write this in black ink so not to scare anybody that doesn't like the red ink color. So what we have is actually 0.02576. We're multiplying by this number, 0.0225. Both of these have no units. We divide by this number. 987 times 10 to the 9, and that has units of coulombs to the minus 2. Okay, that makes sense because coulombs here is in the bottom. Coulombs in the bottom. Now we can calculate this. I'm going to plug into my calculator 0.02576 times 0.0225. Divide all of that by 8.987 times 10 to the 9. Boom. What we get is 6.449 times 10 to the negative 14. This coulombs to the -1 is in the denominator, so I can bring it to the numerator and it'll just be coulomb squared. Remember, this is Q squared. Square root both sides to get Q. Square root this number, and we get 2.53 times 10 to the 1, 2, 3, 4, 6, 7 minus 7. Write that a little better. Coulombs. 2.53 times 10 to the -7 coulombs. Let's see if that's the correct answer in the textbook. Holy guacamole. Hold up, guys. Hold up, guys. We got the wrong answer, and I can already see where it came from. And it is because I... Wait a second. Is this the right answer? Or is this the right problem? So we got the wrong answer. Bruh. My app started to update mid-recording. Alrighty, guys. Welcome back again. And sorry about that last little cutoff. We were doing this problem over here with these two charged particles, 1 and 2. And the last thing I did was I basically solved this problem here, except we got the wrong answer. And I thought originally my mistake was that I did only A inside of the Coulomb law radius thing, when it should have been 2A because it is this entire distance. But then I noticed this over here. The length of each string is 1.50 meters. So that was my mistake for doing this problem very quickly. What they actually tell you is that this length is 0.150 meters. They don't tell you the length of A, but they do tell you this angle, 5 degrees. So I'm gonna just erase this here because this is wrong. We do not have that. Because that is wrong, this is wrong. And then because that is wrong, this is wrong, and so is this, and so is this. So let's just redo that really quick over here on the side. We're gonna have a right angle triangle. Let's draw it like that. Theta here equals 5 degrees. This length is 0.150 meters, and we are looking for this A. So how do we do this? So we can again use SOHCAHTOA. In this case, the angle is here, and what we're looking at is the opposite side, and this here is the hypotenuse. So what we can do is create this equation here. Sorry, just gonna save some space by doing that. We are gonna create sine of 5 degrees is equal to opposite, which is A, over hypotenuse, which is 0.150 meters. Multiply both sides by that 0.150 meters, and we get an equation for A. Meters. This is also a good reason to keep your units again, because sine spits out something that is unitless. So if we have something that is unitless over here multiplied by something with units of meters, we know that on this side of the equation we should get something of units meters. So god damn, bro, I don't have my calculator again. I'm just gonna ask Siri. Sine of 5 degrees. Fuck. Alright guys, give me a second. Alrighty, we are back, and now I have a calculator, and I can finally calculate the length of A. So I'm going to plug in sine of 5 degrees. This gives me 0.08715. Multiply that entire thing by 0.150 meters, and I get a small length of 0.01307. I'm going to round it to 301 meters. This is equal to 1A. What we want is actually 2A. I'll multiply this by 2. 0.0, let's just say 26 meters. So I'm going to plug this back into here, 0.0. Oh, my bad. It's not actually there. Sorry if you're not following along. Basically what I did was made a mistake originally in Coulomb's law, and I put the wrong r squared. Now I have the right one, and it is 0.026 meters. 0.026 squared gives me a value of, now I'm going to replace it down here, which is where the mistake followed through. And this is how you can fix mistakes by 676 meters squared, by just kind of following through with them. So we multiply that on this side, 0.00676. And now we have to calculate this whole thing. So I'm going to do 0.02576 times 0.000676. Divide that entire thing by 8.987. 8.987 times 10 to the 9, close bracket. We get this number here, 1.99376. Let's do 94. All right. Keep 3 sig figs. No worries about sig figs if you don't know what they are. They're not too important in physics classes. I mean, they are, but don't worry about it for this class. Worry about it if you are in a chemistry class. We're going to square root this and get Q is equal to 4.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 10, -8 coulombs. Please be the correct answer. Let's hop into here. 4.42 times 10 to the -8. 4.4 times 10 to the -8. Let's go. We are missing a 2 over here, but that's just because my calculator is limited here. If you convert it to scientific notation, you should get the right answer. So amazing. I hope that was good, guys. I'm sorry I took a bit of a loop-de-loop kind of mistake here, but you know, mistakes happen. Just double check your work. And that's also why it's good to do examples, because you can mess up on the example instead of on a test or on a homework or something. But it's okay to mess up on the homework too. And it's also okay to mess up on a test. You know, we are humans. All right, let's move on to this problem here. And then after that, we just have one more problem. And you know what? I'm going to hammer them all out in this one video here, because it is best to just post all of this in one go. And this one I think will be a bit simpler. So we have a droplet of mass. I'm going to draw the droplet right here. Mass is equal to 3.00. We got times 10 to the -12 kilograms. This is located in the air near the ground during a stormy day. So let's say the ground is right here. It's a stormy day. There's other droplets falling around. At atmospheric electric field of magnitude 6.00. So we have some electric field. I'm just going to write E like this because we're not given the direction. Oh, points vertically downward. Okay, so actually let's do the electric field in blue. Electric field here. I'm just going to draw it. Oh, save some room there for... So this E right here is equal to 6.00 times 10 to the, let's make this a little bigger, times 10 to the 3 newtons per coulomb. This is the SI units for the electric field. It could be written in other units, but we'll get there in another chapter. So that points vertically downwards in the vicinity of the water droplet. The droplet remains suspended at rest in the air. What is the electric charge on the droplet? This is pretty much the same problem as this, except we are simplifying it to just 2 forces. So we have here the droplet of water. There is the force of gravity, which is normally ma from Newton's second law. And force of gravity is just mg, where g is 9.81 meters per second squared. So we are going to rewrite that as 3.00 times 10 to the -12 kilograms, 9.81 meters per second squared. So we can calculate that right away. I feel like it'll be useful. Let's just throw it out there. So we got 3 times 10 to the negative 12. Multiply that by 9.81. Boom. And now we got 2.943 times 10 to the negative 11. Again, we have kilogram meters per second squared, or this is equal to newtons as well. So that's important. Now it's telling us to find the electric charge, and it's also telling us that this droplet is just chilling like that. So in the other example here, I told you that these blue forces pointing up and down vertically, they equal, and we created these equations here. Then the red ones going left and right, they also equal, and that is due to this word equilibrium. So when something is in equilibrium, you know that some forces should cancel. Here we have Fg pointing downwards, and we also have probably Fe, which is coming from charge times the electric field. This electric field here, because the water droplet is charged. How do we know the water droplet is charged? The droplet remains suspended in midair. What is the charge on the water droplet? It's asking us for the question. Also, the droplet wouldn't remain stable in midair if there wasn't any force acting on it. So sometimes you see this problem as, or these equilibrium problems written like this. Sum of all forces, they normally have this I here, is equal to 0. Or you could say Fe pointing up, let's say you call this the positive direction and this the negative direction. Then we have Fe, positive, minus Fg is equal to 0. You could write it like that, sum of all forces equals 0. The way I like to write it is we have one force perfectly equal to and opposite another force. And that is exactly this equation here. If you subtract, if you add Fg on both sides plus Fg, then here we have Fg cancels with this Fg. On this side we have plus Fg, and you get this equation here. Both ways work, and it depends which way you want to do it. Either you could do it this way here, sum of all forces equals 0, or you could do it this way here. Equal and opposite forces must exist for something to be in equilibrium. So both of these work, both of these get you in the right location, in the right solution. And also, both of these could be used for this problem here. The sum of all forces will get you to these equations. So let's see what we get when we expand this equation here, right? So let's put this one here in the middle. We'll work with this one. On the left-hand side, we have, we have Ke. Actually, in this case, we don't have two charges. We have the electric field and this equation here. So I just wrote this equation here. If you remember from my Word document in the last video, that is one of the equations that I gave y'all. This one over here, right? You see this one right here? So this is an equation you're going to see written a lot. Basically, it is just Coulomb's law, except they factor out a Q, and then they write Ke, they write another Q here, R squared, except they call this whole thing the electric field. So instead of writing the equation like that, they write some charge times the electric field. And that's very cool, because what this is telling you is some charge Q inside an electric field E will create a Coulomb force, Fe. So in this case, that's what we got. And that's what we're going to roll with. So we have Q, E equals, and on this side, you'll have mg, but we already calculated that. So we're going to plug that in directly. 2.943 times 10 to the negative 11. We have newtons. On this side, we have Q times E, which is equal to a force, and we know force has units of newtons, so it looks like we're Boolean. And if you want, we can divide both sides by E to get an equation for the charge. 943 11 newtons. What we're going to do here is plug in the equation for the electric field. That is this guy here. I'm going to copy it because I like the color blue for the electric field. It's kind of nice and fitting. And it looks like here, when we flip this fraction around, what we have is newtons times coulombs over newtons. These newtons cancel just like that, and all we're left with is coulombs on the numerator, which is cool because this guy Q is a charge and has units of coulombs. So I'm going to plug this into the calculator. We got 2.943 times 10 to the negative 11. Messed up something on my calculator. Divide that whole thing by 6 times 10 to the 3. And we got 4.905 times 10 to the minus 15 coulombs. Let's check the book if that's correct. Analysis model. Here they kind of do an explanation in the book of where they get these equations from. If you like, you can go through that. It's pretty nice. Let's check out where the problem is. A water droplet, and we get 4.90 times 10 to the minus 15. 4.90 times 10 to the minus 15. The only thing is, there is a minus sign on this charge. And there's a couple ways you could have figured this out. So in the book, what they tell you is that the electric field has a negative sign. And I actually told you guys earlier, let's say that we call this the positive direction and this the negative direction. When you did something like that, in this case, you would have to multiply this by a little negative sign here. Negative sign follows here. When you divide this E, you have a negative sign here, and then you get a negative sign here. Or you could have done this whole thing, and instead of rushing like me, you could have asked yourself, when you were looking at the problem, you were asking yourself why a positive electric field pointing downwards would create a force going upwards. So if this electric field is positive, the only way it can create a force going upwards is if the charged particle that is placed inside that electric field is a negative charge. So a little bit of a mistake on my end. If I solve this problem very quickly on a test and I just wrote this with no minus sign, it would technically be wrong because we are saying it's a positive charge. The water droplet actually has a negative charge. And yeah, just make sure you go through the problem a bit slower than I did. But other than that, you can get the magnitude this way here. So if that problem looks good for y'all and you are fairly comfortable with it, we're going to move on to this final problem here. So we solved pretty much all these problems here together. I know it's a long video, but I think it's good to go through them. And now we are left on to this problem, which I said was an important one. And if you remember, when I showed you guys the summation for the vectors in this problem here, this one, we took quite a while to get through it. So this problem I said is important because it deals with the same thing, addition of vectors. And you can actually see they did a lot of the work for you. Here they have a dotted line creating this vector field line, a dotted line creating this vector field line. And the summation of these two, you can see they also drew these dotted lines and they gave you the resultant vector. In the problem I did, I don't think they showed any of that, but we're going to go through it slowly. So let's read the problem. Charges Q1 and Q2 are located on the x-axis at a distance A and B, respectively, from the origin as shown in figure right here on the side, this one. Find the components of the net electric field at point P, which is at position 0, y. Okay. So first things first, recall, the electric field is calculated using this equation. Ke, Q, R squared. Sometimes there's a little R hat here. This R hat here tells you that the direction of this electric field, because it is a vector, is in the same direction as this line conjoining the points, technically. When you're talking about an electric field, you are talking about a point here, which creates the electric field, a charge, let's say Q, and a point here, a point in space, right? Space, where you are trying to find the electric field. What is the electric field here at this point? So you can create a dotted line connecting these 2 points, much like how you could create this dotted line if this was, for example, a positive charge for Coulomb's law. Remember? So they did this in the problem for you. And, oh, by the way, my explanation for that was this little r hat. So this little r hat, for example, for this vector would be pointing this direction. Remember, something with a hat on top of it is a unit vector, right? It is a unit vector. It is just telling you the direction of something. And this stuff over here is the magnitude. So this gives you magnitude of E. When you multiply this magnitude by this unit vector, then you get the total thing, which is a vector with a specific strength and a specific direction. Not too important to know, as long as you know how to use the equation and solve the problem. But it's just kind of nice knowing what a unit vector is. So, and also you see this little r hat a lot of the times. So now that we know this, right, let's break apart this problem here in a couple of different steps. Let's see if I'm still recording. Okay, looks good. After this, I will end the video and we're going to move on to the next chapter. Alrighty. Oh, we're also given a couple of angles. Theta, phi. Cool. Cool. All right, let's start with E1. E1 is the electric field created by charge Q1 on this point P. And it creates this vector here. So I'm going to do E1 right here, dot, and just start working the problem out over here. Let's do the magnitude first. So E1 is equal to KE times charge Q1. Q1 is not even given to us. Okay. I guess this is a problem where you solve it using some symbols and we don't have any numbers. Okay, we have R1 squared. All right, is that it? Interesting. All right, well, it looks like that's it. Let's think about what this is. This is a vector going in this direction, and what we have is, remember this Cartesian plane here? That's Y. Cartesian coordinate system, my bad. They so conveniently gave us this angle here as phi. All right, so let's say I'm going to move this phi out of the way a little bit and just break apart this guy into its components. So we have this component here and this component here. So remember that this actually is E1. Let's call this E1x, E1y. All right, and then of course we have here phi. So let's remember SOHCAHTOA. Whoops. TOA. So in this case, if we use sine, remember phi this time, we don't have theta. Sine is opposite over hypotenuse. Opposite in this case is this thing here, which is the same thing as this thing, which is E1y. Opposite is E1y over E1. Cool. Now we can multiply E1 on both sides and we get an equation. E1y is equal to E1 sine phi. We could do the same thing for cosine. I'm going to take this, put it right here. Two little lines. Cosine phi is equal to adjacent over hypotenuse. In this case, adjacent is E1x. over E1. Multiply both sides by E1 and we get an equation for E1x is equal to E1 cosine phi. So these are our components here. I really hope this is a problem that uses symbols. Oh. Interesting. So what we could do here is actually simplify both of these equations a little bit more. I'm going to erase these two dotted lines, and we have E1y is equal to, we calculated E1 as this over here, right? So we have KE Q1 R1 squared sine phi. We have the same thing here. E1x is equal to KE Q1 R1 squared cosine phi. And another thing I'm seeing is that R1 here is given to us by this triangle, which is given by A and by Y, right? Because they're telling you that this point P is at the location 0, y. So it's a distance y away. So let's just find this, the value of this R1 in terms of y and A. So it's very simple. R1 squared is equal to Pythagorean theorem, A squared plus Y squared. You guys can see that, right? So that means, well, we don't actually need to solve for the square root of R because we need R squared. So we can, again, replace this entire equation here. E1y is equal to, let's put everything on top to make it a bit more clean. R1 squared is equal to A squared plus Y squared. You guys see what's going on here? It looks a little bit interesting when you're not plugging in numbers, but you know, you're just using some symbols. Shouldn't be too bad. Here we have Q1 cosine phi. And we have R1 squared again, which is A squared plus Y squared. These are now the components of the vector. I don't see any other way we can simplify them further. This is as simple as we can get. So at this stage, we have completed this vector here. Now we can do the exact same thing for this vector here. All right. Looks pretty good. I'm going to draw a line like this. Here we did everything for E1, and now we're going to do everything for E2. So we can just look up and see what we did. We started off with the electric field equation. Here we have Q2, here we have R2 squared, right? R2 squared. And actually, since I know where we're heading, let's do the same thing for this triangle. So we have R2 squared is equal to, in this case, it is B squared. And we also have Y squared, same thing. Okay, pretty nice. All right. We can equate this to the new thing we found. Let's put everything on the numerator again. B squared, Y squared, right? Looks good. All right, now we have a vector that's going this direction. This is E2. We have a Cartesian coordinate system, which is now created like this, all right? Keep in mind, this is, let's say, negative y direction, because we're going in the negative direction, and the angle given to us here is actually this one here. You see how the Cartesian coordinate system is made? Here is the x, and here is the negative y-axis, and this is the vector created, and they give you this theta. I'm just doing this very fast because I have kind of an idea of how to break apart these components, but if it's your first time, you know, don't stress. Go through it slowly. You know, drop a comment if you have a question. So this theta, it's not even given to us, it's just theta. As a symbol, we're going to break apart the vector into the components. So here we have one. Here we have another. And actually what I'm going to do is... My bad, guys. I'm not going to edit out that sneeze. I am not a great editor. So what I'm going to call these guys is similar to the last case, E2X, E2Y. You guys are good with that? So in this case, we have, again, SOHCAHTOA. Let's do sine theta is equal to, and let's look at this. Opposite is equal to E2x over E2. That means that E2x is equal to E2 sine theta. I just used SOHCAHTOA again, and I looked at the triangle, and I found out which side was the opposite, which side is the hypotenuse. The hypotenuse is normally the magnitude of the vector that you're working with. Here, I'm going to draw the whole thing for cosine. Cosine is adjacent over hypotenuse. Oh, my bad. I made a mistake. So these are supposed to be y's because we have opposite over hypotenuse for sine. Opposite is the y, right? The y is over here. That's the opposite side. That's the same length as this vector. So this is a y and this is a y. Now adjacent is the E2x, right? Little mistake. Make sure to catch those before you move forward. You don't want to have a mistake like that all the way at the end of a long problem. It's absolutely annoying to solve it. So E2x is equal to E2 cosine theta. Put two lines there like that. Cool. Now we have E2x. We're going to plug in E2, which is the thing we have here on the top. K E Q2 cosine theta. B squared y squared. E2y is equal to Ke Q2 cosine theta. Y, oh my bad, I should probably do B first. B squared plus y squared. Okay, it looks like we got the same sort of form for these components. And we have these components, we have these components. Let's copy these guys down there. And I guess since we have components of a vector, we can add them all up together to get this final vector in the middle. And we're going to get that vector in terms of a whole bunch of different values. I mean, I don't think it should be a whole bunch of different ones, but let's paste this and let's also draw a picture. It's not drawing a picture because here I just have a ton of symbols. So if you remember, the picture that we have, let's actually look at this picture. Paste, click this, crop. Okay, I'm gonna crop it like that. All right, that looks good. So what we did here was, I'm gonna use this red line. Maybe red was not the best color. Green. Okay, here is one vector. I'm drawing in a squiggly line like that so it's better visible. And here we have another one. This is E1x. This is E1y. Now we're going to have this red color here. This is E2y. And I would say somewhere along the same thing here is E2x. Cool. So what we want to do is combine everything in the y direction, combine everything in the x direction. So we have y direction. We're going to take E1y. I'm just going to take this thing here. E1y, copy that. Paste. Boom. I'm going to put a plus sign here. Actually, let's take the other y2, e2y, this one. Copy that. Paste that there. Combine these two like that, boom. That is the component of our y direction. Now we will do the same thing for the x direction. And I will do this. Let's do both of these in a single paste. So e2x, or let's do e1x first. e1x, e2x. Plus sign. Okay, let's see what the problem is actually asking us. Find the components of the net electric field at point P, which is at this. Okay, well, we have the components. Here they are. Now, I don't know if we can simplify these a little bit more. Sometimes in math, physics problems, they ask you to simplify something quite a lot. In this case, I don't really want to do any simplifying, so I'm just going to erase this in the middle. And we have the x components and the y components. Now, let's actually see if this is the correct answer by looking at this over here. So what we have is the x components. The x components are KE. I'm just looking at the stuff. Oh man, actually I don't want to finesse you guys with any quality problems, so I'm just gonna do this. All right, save that. Let's go back to our original picture. All right, what we're gonna look at is this. 1, x direction, x1x, x2x. Hey, I called them the same thing. We have this thing, which is the cosine of phi. We have the x direction here. So what we have is KE. We have a KE here. Q1, we have a Q1 here. It's magnitude bars, but I don't think it matters because we have... I guess since they're asking us for the net electric field. Okay, so yeah, maybe magnitude bars should have been put here so we avoid the minus sign. It doesn't matter too much. We have KE, we have KE. We have Q1, we have Q1. We have cosine phi, we have cosine phi. On the bottom, we have a squared, plus y squared, plus y squared. Very nice. After that, we have a plus sign. And then we have a KE, we have a KE. Q2, Q2. Again, magnitude bars because otherwise there would be a little minus sign. But the way I did it, I kind of just considered this was a magnitude. You know, we're working with symbols here, right? We have a cosine theta, cosine theta. On the denominator, b squared plus y squared, b squared plus y squared. Cool. X direction is good. Y direction, ey is equal to ey1 plus e2, e1y plus e2y. That's what I did here. So we have the y direction. We have a ke, a ke. We have a q1, q1. Sine phi. Denominator is a squared plus y squared. A squared plus y squared. Here, I have a plus sign, and they have a minus sign. Very interesting. Now, why is that the case? Because I'm a dingle bob, and I forgot that this thing is going in the minus direction. So a little mistake there. I'm going to correct that. That would be probably minus 1 point on the test. Sorry about that, guys. But yeah, we have a minus sign there because in the y direction, one vector... Whoa, didn't want to erase that. One vector is going in the vertical direction. One vector here is going in the negative y direction. For the x direction, we had both of these as positives because they were both going in the positive x direction. You don't have a case like this where they're going in opposite directions. So yeah, this minus sign, important. Now, the first term here is correct. The minus sign here was incorrect. But let's check the rest. KE, KE, Q2, Q2. Ooh. Interesting. Cosine of theta. This is incorrect here. We have b squared plus y squared on the bottom, but we have a sine theta, or they have a sine theta, and we do not. So what did I do wrong here? What I did was, we have the y direction, right? This is the component from this vector, because we are dealing with this b squared, right? This b squared came from here, and what we are looking at is breaking apart this vector here. So I broke it down like this, and I said EY is equal to adjacent, no, sorry, I said EY is equal to opposite over hypotenuse. Opposite over hypotenuse. E2y. E2y. Bro, this is crazy. Look at this. I have an E2y over here. E2y is equal to E2 times sine of theta. And then what I did here was, I have an E2y. Here I have everything except I changed this cosine, or this sine, to a cosine. Why did I do that? Maybe it's because all the copying and pasting I did willy-nilly. So yeah, sorry about that too, guys. Another little mistake. Man, so I actually would have gotten a couple things wrong with this problem. And yeah, let me just correct that over here. So what we have is the y direction. Boom. This guy should actually be a sine. Interesting. But you guys see how this problem works, right? They have a bunch of symbols, and it was a little bit strange, but technically this is what you did in this problem here. This one here. Except here they didn't have symbols, they had all the numbers given to you, and you could pretty much calculate for everything. And I think I made some mistakes in that problem too on the first hand. But this one here was very weird, so sorry about that copying and pasting. Let's take a look. They say evaluate for B, section B. Evaluate the electric field at point P in the special case that Q1 is equal to Q2 and A is equal to B. It's actually an interesting point. A is equal to B. So yeah, if A is equal to B, the denominators, I guess, would be equal, and you can kind of simplify the case a little bit. Should we do that problem? I think the video is already becoming too long, and it is getting quite late for me, guys. And as you can see, I'm making some silly mistakes copying and pasting. So I will just leave this problem here as is. If you want, you can do part B. If you want, you can leave a comment down below and let me know if you want to do it as well. The answer we got was this. And as you saw, I made a couple mistakes, but just a quick refresher of everything we did. So we started off with this electron and proton problem in the hydrogen atom. As you saw, it started off very easy. It was just plug and chug, get numbers, check units, good to go. This problem was quite long because I had to show you how to break apart vectors. But again, plug and chug, basically use this equation here, and as long as you can break apart vectors in this form and figure stuff out with triangles, you can add vectors up like this. You can break apart triangles using SOHCAHTOA. You should be good. I went through that problem quite lengthy-wise. This problem here was also very nice. The main thing here is equilibrium. So when equilibrium is the case, you normally have some kind of equations that equate like this. As you saw, these red bubbles, those equations equate, and then these blue bubbles here, these equations equate. Sometimes there's a minus sign or a plus sign here or there that you're missing, but also make sure that you read the problem nicely, because what I made a stupid mistake on was I just saw this number 1.50 and I thought that was A. So I made a mistake 2 times there. That number is actually this. And what you need is A. So you need to use this triangle here. You need to use this angle, some SOHCAHTOA trigonometry. And you need to find the right answer for A. And then you need to actually take 2A and plug that into the Coulomb equation for R squared, which was right here. The next problem was this water droplet. Again, fairly simple. Equate forces. So the force in this direction, the force in this direction. Remember, directions matter, and because they matter, and because electric fields that are positive can only create a force acting in the opposite direction of the electric field if the charge is opposite, that gives us the sign of the charge. So you could also just use this equation here as shown below. And also remember that the directions you choose, those have an effect on this minus sign. So whatever way you like looking at it, maybe how I'm explaining it might be a bit confusing. It's good to have kind of your own way of thinking of where these minus signs come from, because there's a bunch of different ways of looking at it. Either perspective, choice of direction, or choice of coordinate system, or you could just look at the problem and see that it's a positive electric field. There's a force going downwards. The electric field is positive and it's also pointing downwards. So the force that the charge must feel is going upwards. How is a electric field that points downwards creating an upward force? Well, the charge of the thing, the water droplet in this case, must be opposite of the electric field acting on it. That is something maybe you might learn after a couple of problems, after a couple of mistakes, kind of like how I made it. But as you saw, I made a mistake here, and it could happen to anyone, right? So this problem here, we got the electric field due to two charges. It is an interesting problem because all they give you is symbols. And with these symbols, as you can see, you get some thick looking equations here. Don't worry about it. The equations, this is kind of why you keep units. If you kept units in your problem, they would also look like these weird kind of equations. But normally, people just plug in numbers, no units. But as you can see, these problems here, it is pretty much the same thing we did in that first problem. Break apart vectors, add them up, and also keep in mind the directions of all your vectors, and don't copy and paste like I did here. I think that was the mistake I made with this sign. If you do that, you should be good to go. So yeah, guys, I hope that was helpful. I'm going to go back to this book here because the book now ends. I think there's this part of the problem. Find the electric field due to an electric dipole. Interesting. So this thing here with a positive charge and a negative charge equally distributed by a distance A is an electric dipole. Good problem, but my video now is probably getting very long. And also we didn't get to the electric field line section, which is probably going to be something that could have helped you out with the charge mistake I made for this problem. So anywho, if you go through this book here, try some of the problems out at the end of the book as well. I also haven't gone through any of the motion of a charged particle, so maybe I'll do a video on these, but it'll most likely be a different day. Yeah, I hope that was helpful. Take a look at some of these problems. Take a look at the end of the chapter. This is pretty much what I looked at to create a little study guide for this chapter. I think it's pretty helpful. It's kind of like a equation sheet. We got electric charge and some of its properties. We got some stuff on conductors and insulators, which I haven't talked about at all in these videos. And some other stuff that I spoke about. This nice equation, pretty simple one. And then also some other problems here that you can go through in the book. So yeah, maybe I'll go through some of these. There are a lot of problems here. And I think if I spend the time that I do for these problems, I'll have quite a long video to go through. So let me know if you guys want to go through that. And then the next chapter we'll go through, I already did a video on Gauss's law, so you should see that posted publicly soon. And I will do a section on the continuous charge distributions. And then after that, we're going to head to the electric potential, which is chapter 24. So I hope that was helpful, guys. Have a good one. Sleep tight. stay hydrated, keep focusing on physics. Physics is great, and good luck.